Hey pioneers, great that you're here. Today's lecture is on testing off-chain code with Lucid. And without further ado, let's get into it. As a recap, the script that we are going to write and test some off-chain code for is the -r timed script located in week 6 in the lecture folder. In this validator, a user can send funds to the script with a deadline in its datum. Once this deadline is reached, anyone can claim these funds if they provide an integer equal or smaller than 0 in the redeemer. That is captured in these two lines. Before we go into creating the off-chain code and tests, we will first take a look at the tools that we'll use. These tools can be divided into 3 categories. The first is the software that we're testing, which will be the Lucid emulator. Next, we have a native implementation for unit testing in Dino. And lastly, we have FastCheck, a property-based testing tool written in JavaScript, similar to QuickCheck, the Haskell library for property-based testing. If we look at Lucid, the emulator, we see that it implements a provider, similar to Blockfrost that we saw in previous lectures. The difference is that this emulator can be set up to run a local mocked blockchain to run tests quickly and in our full control. Similar to Blockfrost, this emulator has methods for querying the mocked blockchain, submitting transactions, but also methods for controlling the progress of this mocked blockchain. This can be done via the await block and await slot method. These will allow us to emulate our contract and off-chain code. Before we can write our off-chain code for testing, we need to write the validator to our file system. To do so, we first change directory to week 6. In this folder, we then open a Cabal REPL. Once this is done, we'll import 2 modules. First, utilities module, and the second, the -r timed module, which contains our validator. Next, we'll write our validator to the location in the assets folder, and we'll call it -timedr.plutus. And the validator that we'll write is called validator, located just below here on line 42. So if we press enter, we see that it's written to that location, and we have our validator located here that we can use. Now that we have our script, we can copy this and start with off-chain coding. Similar to the previous lectures, I've created a -rtimed.ts file located in this folder, lectures tests. If you look at that, we see that I import 3 things. The first is Lucid, which I import as the letter L. Then I import something from the standard testing library of Dino, and I import the FastCheck library as FC. Then I define what our script is, namely the CBOR hex that I just mentioned in this file. And then I also convert that script to an address with Lucid. And note that I do not initiate Lucid yet as a constant, but I just use it inline, and you'll see why I do that in a moment. Next, what we do is we define our datum, and we have a type datum that is type deadline, or it's a wrapper around a deadline, which is just an integer. And we also have a typed redeemer, which is just an integer. And once those are defined, let's look at the function send_to_script. This function sends funds to the script location with a datum. And if we look at the inputs, it actually, besides the datum, needs more. It needs a private key as well to sign the transaction, and Lucid. Note that I use a private key here because we're emulating something. And this is due for reasons that we'll see soon. So with that, transaction is pretty simple. We set the wallet in Lucid, we create a new transaction and pay to the contract, and we send an inline datum that is typed, of course, that's our datum. And we send an amount of 10 ADA to the address. And we sign it and then we send it. So this is the send function. And we also have a grab function, which is similar. But besides taking in a Lucid instance, it also takes in an emulator, private key, a datum, and a redeemer, of course. So what this function does is it first selects our wallet, then it converts the redeemer to CBOR encoded string. Then it looks at the mocked blockchain and the address that we have created for the script, and it fetches all the UTXOs at that script. Then it filters these UTXOs for UTXOs that have a certain datum, namely the datum that we want, that we have the deadline for. And if we find some datums, so the list exists and it's not empty, then we can construct a transaction that claims all the UTXOs. So we claim all these UTXOs denoted by our UTXOs with our redeemer. And we attach the validator, of course. And instead of the date.now, we do emulate.now. And what this does is it fetches the current time, in POSIX time, of the emulator, and it attaches that to the transaction. We need this because our transaction uses the script -r timed. And this validator checks time, so it will check our transaction validity interval. So we have to appropriately construct our transaction to make our transaction valid. Then we sign the transaction and submit it. And lastly, in the case that we did not find a UTXO at the script with our datum, we throw an error. And we throw this error because we're testing. And in our test that we'll soon see, we first send something. And if that is not found, our test failed. So we need to throw an error. So let's see a function that runs a test. And this function has 3 inputs. It has a datum, a redeemer, and a number n. And what this number n is, it is the slot number at which the grab function will be initiated. So if that is before the deadline, the transaction should fail. And if it's after, given a correct redeemer, it should process successfully. And now it will become clear why I did not initiate Lucid, because we're going to set up an emulator. And to do that, I will first define 2 users, and I will generate a private key for each of these. Then I will get their addresses. And again, I will not initiate Lucid or save it to a constant. And I do that as well for user 2. And then given these addresses, we can set up an emulator. And this emulator is defined as the following function. So we define a new emulator. And this takes in a list of outputs that we want to create at the genesis block when our emulator runs. So we define an address, namely address 1. And at this address, we want certain assets. And the assets that we want at this address is 10,000 ADA. And that's this in Loveless. And besides address 1, we also have address 2, which we also grant the same amount of ADA. Then we initiate Lucid and store it. And we initiate it with the provider emulator that we just defined. This sets the stage for testing. And to test, it's really simple. We can now pass this emulator and Lucid through our function send to script and grab funds to initiate it. This while also controlling how and when transactions are sent. For example, in our test, we first send something to the script. So we provide our Lucid instance. We send it as user 1, and we send our datum that was parameterized in our function. Then we wait n slots, and then initiate the grab function. Again, we give it Lucid, the emulator, but this time we let user 2 grab the funds with a datum and a redeemer specified as inputs of this function. And then again, we wait 10 blocks to pass. So let's see that in action. So what we can do is we can comment out this line. And let's also comment out the line that fetches the balance of address 2 at the end of this emulation at the end of our process. And if everything goes correct, what will happen is user 1 will send 10 ADA to the script address, and after n slots, user 2 will grab that. So user 2 will have more money. So what we then do is we run a test, and the test that we're gonna run has the following inputs. First, we set our deadline as a big integer that wraps around these numbers, and I've formatted in this way because this date is in milliseconds, and on average a block is processed every 20 seconds, which is 20,000 milliseconds. So the deadline is now set at 5 blocks plus 1 slot from the initiation of the creation of our mocked blockchain. And the redeemer that we're gonna use is -42, which is indeed a negative number. And the moment that we're gonna call our grep function is at slot, well, that should be 5 blocks after the deadline plus 1, so that when the deadline passes, we immediately send a transaction. So if I save this and then quit this and do dino run, we get the following back. So I've logged in line 88 the address of user 2 at the end, and we see that the amount of loveless at this address has increased by 9.6 ADA, which is due to transaction costs less than 10 ADA, but we indeed see that user 2 successfully grabbed the funds. Now we can also alter this function so that user 2 grabs the funds too early. 1 slot before the deadline, he sends a transaction. If we then run it, we get an error. We get a Plutus error that the validation did not succeed, and that's because we grabbed the function too soon. Now that we have written the test environment via the Lucid emulator, we are ready to write unit tests. Before we do that, let me comment out this real quick to make sure it isn't run again. So in unit testing, we have 2 types of tests. Tests that we expect to fail and tests that we expect to succeed. In the Dino test environment, we can wrap functions and capture their errors when they appear. And when a test fails, for example, that we expect to succeed, this function will grab that error and log that the test that we denote by the string failed. So the deno test function takes in a string that is used to display the test. It will take a function that runs something, namely the test. It will await that, and if it fails, it will log that it fails. If it succeeds, it will just mention that the test successfully ran. And we put this in a wrapper function for the inputs that we use for the run test function. Now, on the other hand, when we expect a function to fail, we use the test fail function. This has the same inputs, but it runs a bit different. Inside the test environment of Dino, we have a function, but because we expect this function to fail, we have to capture that. So how we do this is we define an error thrown boolean that we set to false. Then we try and await the run test, and we expect this to fail. So if it fails, we catch the error and we set the error thrown value to true. If the test didn't fail, then the error would not appear, and this would be skipped, and the value would still be false, or the error thrown value. Next, after that is done, we assert that the error thrown value is true, and if not, we throw an error that the test failed, though we expected the function to fail. So let's see which tests we can do. So I've written here some unit tests, 2 that should succeed and 4 that will fail, or we expect to fail. And the ones that we expect to succeed are of course always after the deadline. And the redeemers that we use are negative or 0. And the ones that we expect to fail are either positive or before the deadline. So that's these. And we can run these tests via the following argument, deno test. And if we run that, we see that it's running 9 tests. And we see that the unit tests display the string that we put here. And we see that they all process OK, and also the time that they take. And we see that they succeed. Now we can make things such that they fail. For example, we expect the test success function to succeed in grabbing the funds, but we can manually alter this to be before the deadline. So we expect the test to fail now, and if we run it again, we indeed see that this test failed because we tried to grab funds before the deadline. So let's run that again, see that it works again, and it works. Besides the unit test that we defined here, you also see that it's running 3 property tests, and namely for negative redeemers after the deadline always succeed, positive redeemers after the deadline always fail, and anything before the deadline always fails, similar to the other lecture. These properties tests are written in the fast check library that I imported, and they are defined here. So let's go through that. So initially, for property tests to run, you have to define how tests are generated. And we do that via these constants that describe how each value is generated. For example, take the negative big integer arbitrary constant. This is generated via the function bigInt n inside of the fastcheck library. And what this function does, it generates integers between a lower bound and an upper bound. And the bound that I set is integers of 265 bits that can either be positive or negative. And then I apply a filter to it. Namely, I filter out all the positive elements. So only the elements smaller or equal to 0 remain. Then for the positive big integers, I do the same, but I filter out all the elements that are smaller than 0 or equal. So what remains are the integers bigger than 0. And similarly for the deadline, given a deadline that is now set at slot 100, because remember that one slot takes 1 second, which is 1000 milliseconds. So if that's the deadline, then elements after the deadline are the integers that are bigger or equal than the deadline. And similarly, slots that are before the deadline are the integers that are smaller than the deadline. Now onto the tests. So for a property test, we have the following. We also wrap this in the deno test environment, and we give our test a name. And for the function, we have something different because we use the fast check library for this, and specifically the assert function. This assert function expects 2 inputs, a property, which is asynchronous in our case, and the number of runs that we have set to 100. And if we look at the property, we see that this again has a function in it, which is asynchronous. And this function has as inputs the redeemer, which is a big integer, and a number n, which represents the slot at which we grab the funds. And what it tries to do, it tries to await the run test for these parameters. And if there's an error, it catches that and it logs it. And it tries to do this 100 times. And for each time, it generates its inputs from these generators. So here we have the negative big integer arbitrary constant that we defined up here, which will only generate negative redeemers. Similarly, it will only generate slots that are after the deadline. And so what this function does, it tests that negative redeemers after the deadline always succeed. So no error is thrown. Then to the next test. Here we have again a property, and the property that we test is that positive redeemers after the deadline always fail. So we check that we use the positive redeemers, and we generate slots after the deadline, and it's the same function. But here we expect it to fail. So similarly to the unit tests, we set a value error thrown to false, and if an error is caught, we set it to true, and we expect that. So we assert at the end that it's true, and if not, we make sure that the assertion here has an error to capture. Again, this is run 100 times. And lastly, we have a property test that tests that anything before the deadline always fails. So we generate slots before the deadline, and the redeemer, it doesn't matter if it's positive or negative. So what we specifically do is we generate numbers positive and negative here. We do not put a filter on top of it. And of course, we expect it to fail, so we use the trick again to capture that it fails. So if we run the test again, we see that it all succeeds because we rewrote the test properly and the script works. But we can manually make it fail, for example, by filtering wrongly. So for example, for the negative integers that we generate, we can make it the bound a bit higher so that the positive integers 0 to 10 are included as well. So let's see if 100 tests actually generate a number in that range, and let's see if it fails. So it actually succeeded because it's still testing for 100 runs. So it might be the case that it didn't generate a number in that range. So let's run it again. And indeed, it fails. So it fails with a counterexample. And the counterexample is 1, which is indeed in the range because we altered it to 10. So it's smaller than 10. And the deadline that it picks is slot 100, which is after the deadline or at the deadline to be precise. And this should fail indeed. So let's replace that again and run it. And now everything works again. So as a small recap, what we did in this lecture, first we wrote a test environment in the Lucid emulator so that we can run tests of our validator. Then we used the Dino test environment to write unit tests. And lastly, we used the fast-check property test environment to write property tests to generate tests for our validator. I hope you enjoyed this lecture, and see you next time.